Okay, so this is the promise activity that I'm going to share with you prior to your exam. So basically, in this video, we're going to find the resultant vector of the three vectors KIM. The first vector is vector K, 20 meters, 30 degrees south of west. The second vector is vector I, 40 meters, 60 degrees east of south. The third one is 50 meters, 60 degrees east of north. We're going to do this using the analytic method. Now, if you can recall, the first step in doing analytic method is to simply try to visualize your vector, and it will make sense why this is something that I highly recommend doing. So the first one is we have to create our um, Cartesian plane, which indicates our directions. So in this case, I'm just going to label the direction. So this should be my north, this is my south, this is my east, and my west. So the first vector is vector k. So vector k is 20 meters, 30 degrees south of west. That means I have to start from west going south. Now, this is my west here. So I have to measure the 30 degrees from west going south, as I've said. So this is how it should look like. Okay, sorry. This one. So maybe that. So this is your angle, and this is your vector k. Second one is I'm just going to do this using the tail to tip or tip to tail method. And as you can see, I'm no longer scaling because this is, after all, analytic method. The second vector is vector I. It's east of south, so from south going east. So this is how it should look like. I'm just estimating it. So since this is 40 meters, this should be twice as long as the first vector. So that is your vector I. And the angle is from here. And yeah, say theta 2. And let's just call this one theta sub 1. And then we do another small Cartesian plane there. And then the third vector is the red one is vector M. It's 60 degrees east of north, so meaning that from north going east. So this should look like this, and since it's 50 meters, so it's slightly smaller than the green vector or vector I. So maybe like that one. Again, I'm just doing estimation because you will see why I did this. Now the next one is after doing that one, if you can recall from our discussion, your resultant vector is actually from your very first origin up to the tip or head of the very last vector, and that is your resultant vector R. Now here's the catch about doing this one. Notice that from the sketch, your vector R is actually found in the fourth quadrant. This is telling you that supposedly, or it should be that your Rx, which is the sum of all the x components, it should have a sign, since it's in the fourth quadrant, to be positive, and Ry should have a value of negative, meaning after you add up all the y components, you should get negative. Now, these are things that are somehow an indicator of whether we're on the right path of our calculation, and this will be very important later. At this point now, we will do the calculation of the components. So to calculate the components, I highly recommend in our worksheet, right, that you sketch your vector, although you don't have to scale it anymore. This is simply for visualization purposes. So this is for vector k. Vector k is 30 degrees south of west. So this is north, south. Just be consistent with your direction, west. And this is how it should look like. This should be your vector k. Now, another thing that you need to be very specific here is to indicate where are the components. So if you can notice, I will draw a parallel line to the x-axis, and that is my, if you can recall, that is what I call my k sub x, or the x component. And I'll draw another parallel line to the y-axis passing through the head of that vector, and that is my y component, k sub y. Now, if this portion here is k sub x, that is telling you that similarly, this over here should also be k sub x, and this over here should also be k sub y. So once everything is set, we can now solve the components. Now to solve for the components, okay, sorry. I actually failed to indicate the angle, which is very important. That's 30 degrees. Now, to solve for the component, you just have to look into the relationship or how our theta and the specific component, let's say in this case, k sub x, are positioned. And from the sketch, it's very clear that this is our angle theta, the 30 degrees, and k sub x is this portion over here. And they are in Bisaya, tapad or adjacent. So adjacent. So I'm going to note here that they are adjacent with each other. And take note that of our mnemonic, so ka, it's the ka mnemonic that has the adjacent side. So that is telling you that the cosine, since it's ka, the cosine of the angle theta is equal to the adjacent side over the hypotenuse side. Now we're just going to fill in the values of the angles and the length. So the angle is 30 degrees, so there should be cosine of 30 is equal to, if you look into that one, the adjacent side is kx. But then again, you have to remember that it's negative kx, since if you can notice, this vector is on the quadrant 3. So another thing or technique that I will tell you is you can write it here very small. The x should be negative, the y should also be negative since it's on quadrant 3, because the components will have the same signs, whether it's on the quadrant 1 or quadrant 3. Now the hypotenuse, if you can see from the illustration, is clearly the magnitude of your vector k, or the vector itself. So dealing with this one, you get k cosine of 30 degrees is equal to negative kx. So what you're going to do is to simply multiply both sides by negative 1. So you can now have an expression like this: kx is equal to the negative k cosine of 30 degrees. Now, I'm hoping you are now very familiar with the unit circle, because this will come in handy. That means to say kx is simply going to be negative. The value of k here, if you can see, is 20 meters, so negative 20 meters, and the cosine of 30 is just square root of 3 over 2. Now, when you simplify that one, that will give you kx is negative 20 square root of 3 all over 2. Do not forget the unit meters. And that could be further simplified into negative 10 square root of 3 meters. So there you go. You have solved for the x component of your first vector. I don't know why it's not doing that. Okay. Yeah. So automatically, the other component, which is the y component, if you're sure that's the other component is cosine, it should be sine. So sine of theta is sol, right? So opposite over hypotenuse. So we do the same thing. Replace the angles and the length. So this is going to be the sine of 30 degrees. And looking back at our sketch of the vector, the opposite with respect to this angle is your k sub y. So that's going to be k sub y. But remember, it should bear a negative sign because it's on the third quadrant. Negative k sub y of the hypotenuse, which is the vector k. Now, if you notice, I am very, very specific about the signs because this could break everything. Like, once you get your one sign wrong, everything is just destroyed. So you have to be very specific and very careful about the signs. So this will be k sine of 30 degrees is equal to negative k sub y, or the y component of k. You simply multiply both sides of your equation by negative 1. So you have now k sub y is equal to negative k of sine 30 degrees. Substitute the values. Negative k is just negative 20 meters. The sine of 30 from your unit circle, if you're very familiar, that's 1/2. So that means to say that your k sub y is just negative 10 meters, because that's 20 divided by 2, or 20 times 1/2. All right. Okay, it's not doing the rectangle thing. Okay, that's good. Now, to proceed with the second vector, you actually do the same thing. So for the second vector, 40 meters, 60 degrees east of south, we start with visualizing the vector. So let's do this together. So you create your Cartesian plane. Okay, so this is your Cartesian plane. And take note that you have to be consistent with your directions. So for my first vector, this is my north. So that should be the same direction on my second vector and the succeeding vectors. All right. Now it's east of south. So I'll start from south going east. So it should look like this one. Yeah. You don't have to scale anymore. This is purely for visualization purposes of your vector. So that's 60 degrees. And again, remember that if I'm going to draw a straight line passing through the head of the vector parallel to the x component, that's gonna be my, this is vector I, that's gonna be my x component of that vector or I sub x. Now doing the same thing along the y-axis, it's gonna give me my y component, and I should name it appropriately as I sub y. Now if this portion over here is I sub x, I'm hoping you now understood, because I keep on repeating this one, and this portion must also be I sub x. If this here is I sub y, they should also be I sub y, meaning they should be equal in length. Now take note, you can write it here so that you will not mess up with the signs. This is on the fourth quadrant, so the x has positive values while the y have negative values. Okay. Once we are set with our illustration, we are now down to solving for the components. So again, the very essential question, you just look into your angle theta and the first component, which is your I sub x. So if you notice, I always start with x so that I will not get confused. And looking at the vector here, 60 degrees is over here, ix is over here, and clearly they are opposite with each other. So I'm going to note opposite here. And from our mnemonics for the trigonometric function, it's so ka. The only function that has opposite there is so, or so, meaning I'm going to use sine in this case. It means to say that the sine of theta is equal to the opposite over hypotenuse. I'm just going to substitute the appropriate values. The theta in this case is 60 degrees. The opposite side of the angle theta is I sub x, and that should be positive here, all over the hypotenuse, which turns out to be just the magnitude of the vector I. So from here, I will get I sub x is simply I sine of 60 degrees. So it's just a matter of cross multiplication. So substitute the values. Your vector I is just 40 meters. And I'm hoping you're very familiar again with the unit circle. The sine of 60 is just square root of 3 over 2. So your I sub x is equal to 40 square root of 3. That's all over 2, included the 40. Do not forget the units meters, and that can be further simplified into 20 square root of 3 meters. So that right there is your x component. Let's do the y component. So that's gonna be the cosine of the angle is equal to the adjacent side over the hypotenuse side. All right. So simply substituting the values, you get cosine of 60 degrees. And looking again at the vector, the adjacent side is I sub y, or the y component of the vector. So you get I sub y. And the hypotenuse is the same, the vector I itself. But again, remember that your I sub y, this portion here, is along the quadrant 4, and the values of the y's there are negative. Therefore, this should bear a negative sign. And do not really forget that. That will really change many things in your answer. So continuing, you get I cosine of 60 degrees is equal to negative I sub y. Simply multiply both sides of the equation by -1. So you end up with I sub y is equal to negative I cosine of 60 degrees. Substitute the values. It's just gonna be, it's just gonna be the negative, and I is 40 meters. And again, the unit circle, remember the unit circle, the cosine of 60 is just 1/2. So it's very clear that I sub y will simply give you negative 20 meters. Just going to put a box over there. All right. So basically, what you did on the first vector, you did the same thing on the second vector. You just have to be very careful with the sign. And when I say very careful, I can't stress it enough, but you have to be very, very careful. Because once you get one sign messed up in either of the components, your resultant vector will be wrong. So for the third vector, it's vector m, 50 meters, 60 degrees east of north. So it should look like this. Is north, south, east, west, east of north, meaning starting north, going east, and 60 degrees. All right. So this one is 60 degrees. And this is your vector m, the name of the vector. And we have to identify its component. So you draw a parallel line. You draw a straight line parallel to the y axis. Okay, I have to make it straight like this one, hoping that's better. And you call that your m sub y. You do the same thing along the x-axis, and okay, it's not working. X-axis. Here, wait. So like this, along the x-axis, and you get your m sub x, or the x component of that vector. All right. So now again, we start with the same thing with what we did. We look at theta and the first component that we want, which is m sub x, and identify their relationship. So theta is 60 degrees, this one over here, and m sub x is opposite to that angle. So you note here opposite. But I actually have to again specify that the x here, the x component should be positive and the y component should be positive. Okay, so if it's opposite, by now it should be clear that the only trigonometric function with O or opposite there is from harmonics. So that means to say I'm going to use sine. Sine of theta is simply the opposite over hypotenuse. Substitute the angle on the legs, so sine of 60 degrees. The opposite of 60 degrees is m sub x. So that's going to be m sub x, positive m sub x, all over the vector m itself. So m sub x will simply be m sine of 60 degrees. So now it's only a matter of substitution. Your magnitude of vector m is 50 meters. And your dear old unit circle, sine of 60 is square root of 3 all over 2. So m sub x will give you 50 square root of 3, everything all over 2. Do not forget the units, meters. So in this case, this can be further simplified into 25 square root of 3 meters. So that's your x component. And of course, for the y component, we do the same thing. Cosine theta is equal to adjacent over hypotenuse. So replace the angle in the lens. Cosine of 60 degrees. Looking back at your sketch, so that means your sketch is very important. If it's wrongly sketched, you get the wrong adjacent, you get the wrong hypotenuse side, so, or opposite side. So you go back to your sketch. This is your 60 degrees. Adjacent to that is your m sub x, because as I've said, if this portion here is m sub x, this portion here should also be m sub x. If this portion is m sub y, this portion should also be m sub y. And looking at that, it's clear that your theta adjacent side is m sub y. So you substitute that here, so that's going to be m sub y positive because it's on a quadrant 1 all over the hypotenuse, which is just m. Because it's very clear, this is your 90 degrees, this one is your 90 degrees, so opposite to that should be the hypotenuse, which happens to be the vector itself. So you get m sub y to be m cosine of 60. And substitute the values. The vector m is just 50 meters. And then the cosine of 60, your old unit circle, that's just 1/2. So it's very clear that your m sub y, the y component of vector m, is simply 25 meters. And you box that one. Okay, so that's how you just solve your vector. And if However, I don't know why the rectangle thing is not working. Yeah, it's really not working and it's annoying me. Oh god. Okay, that's good. So that's just how you identify whether you sine or cosine. How do you identify it? You simply ask yourself, how are the angle and that specific component, say x or y component, related? If it's adjacent, then you use cosine. Otherwise, in this case, if they are opposite with each other, you use sine. So at this point, we're now ready to solve for the r sub x, or the summation of all the x component. So I'm going to write here r sub x. And if you can recall in class, that's just gonna be kx plus ix plus a third vector m sub x. So basically, r sub x is just telling you to sum up all the x component. Or you can think of it as the summation of, say, r sub x. So looking back at our answers, you get kx to be negative 10 square root of 3 meters. Your I sub x is simply 20 square root of 3 meters. Your m sub x is 25 square root of 3 meters. Now we'll do a simple algebra here. Notice that each of these terms over here has a common term of square root of 3. To simplify this, I'm going to factor that out. So I factor out square root of 3. So what is left now will be 10 for the first term, 20, positive 20 for the second term, and 25 for the third term. And do not forget the units. So from here, I just have to evaluate the square root of 3. What is left would be negative 10 plus 20. It's positive 10 plus 25. So that's positive 35 meters. So rewriting that one into a more friendlier option. So that's going to be 35 square root of 3 meters. And you just have to express it that way. Do not express it in decimal. R sub y is practically the same, except you're simply adding all the y components of all the vectors. So it's k sub y, I sub y, plus m sub y. Looking back at our answers, k sub y is negative 10 meters. Your I sub y is negative 20 meters. And your your m sub y is positive 25 meters. So that means that your r sub y will simply be, evaluate, negative 10 plus negative 20, they have the same sign, so basically adapt the number and take the same sign. So it's gonna be negative 30 meters plus 25, so it's gonna be negative 5, right? Negative 5 meters. Now here's the catch. Notice earlier that we actually tried to sketch, although very crudely, just to approximate, no scaling required, the resultant vector, and we notice that our resultant vector is somewhere here. It's on the fourth quadrant, therefore the components must be positive for x and negative for y. Now, to check whether our answers are making sense, notice that our rx bears positive sign and ry bears a negative sign. So this is a very good telltale sign that you're actually doing your calculations right. Because from the geometric method or approximation, it should be on the third quadrant where rx is positive and ry is negative. So since we get these values, we're actually doing good. Now the next one is to solve for the resultant vector. And another way of thinking about the resultant vector is like this one. You draw again another Cartesian plane, and notice that your Rx is actually positive. So this is telling you that this one is moving towards the right because those are the values for positive x. And you do tail to tip. Ry is negative, so that's gonna be going down. So that's Ry. And this is telling you that the resultant vector is just like this. This is your r, and this should be the angle theta of your resultant vector. Now, I'm not going to explain this further, but I'm hoping it's apparent that if you're getting for the resultant vector, you simply get this one, the square root of rx squared plus ry squared, And this is basically just your Pythagorean theorem. Now, if you're not convinced, recall the Pythagorean theorem says that the square of the hypotenuse is equal to the sum of the squares of the opposite side and the adjacent side. Now, in the context of this specific right triangle that you're getting, the hypotenuse, which is opposite to the 90 degrees, is your r. So you get r squared. The opposite side is, with respect to this angle theta here, is ry. So you just get ry squared plus the adjacent side is rx. So you get rx squared. Now, take note that addition commutes, so I can just write this right-hand side of the equation as rx squared plus ry squared. I should have an arrow over there. So when you just take r, you simply take the square root. So you get rx squared plus ry squared. And that is why we tried to discuss Pythagorean theorem in the very first class of physics. So this one is just exactly this thing. That's why the more like the formula for solving for the resultant vector is really like this, and the trigonometry of how why that work is this portion over here. So what you have to do is to simply take this part, take this as your formula. So every time you're asked to solve for the resultant vector, automatically you use that one. And I'm hoping if you're being asked why, then you explain it using this portion here. So you simply substitute the values in this case. Your Rx is just 35 square root of 3 meters squared plus negative 5 meter quantity squared. You have to be very careful in plugging in these values in your calculator because you should use a grouping symbol in this case because the square is distributed to both 35 and square root of 3. So you use parentheses in your calculator. So when you try to plug in those values in your calculator, your resultant vector will give you 10 square root of 37 meters, and that is approximately equal to 60.83 meters. So that's your resultant vector. Now, we are now in a position to solve for the angle theta over here. And if you can recall, you're going to use tangent actually, or I'm just going to write it here. We know as a formula that the way to find theta or the angle of the resultant vector is simply tangent inverse of the absolute value of your ry all over rx. Now, I'm just going to briefly explain why that is the formula. So if you're looking at your geometry over here, you notice that when you're trying to solve for the tangent of theta, it's TOA, right? That's opposite over adjacent. So tangent of theta, the opposite side is actually this one, that's ry. And then adjacent side is this portion over here, that's rx. So if I'm going to find for the angle theta, I think I've mentioned this in class, that what you're going to do is to apply both sides tangent inverse, so that on the left hand side of the equation you end up with the angle theta itself, and on the right hand side you get tan inverse of ry all over rx. So that is why for every calculation of the resultant vector's direction or theta, you end up using this one, and the explanation is found over here and over here. All right, so every time you simply have to more like familiarize or memorize this part here, and I'm hoping you can explain why we use that one. So going back here to the purely physics part, so theta is tangent inverse of ry, and ry is just negative 5 meters all over 10 square root of 37. Sorry, it's 35 square root of 3. 35 square root of 3 meters. And notice that the units cancel out because that should be the case always if you're getting the trigonometric function. So theta is just gonna be equal to 4.58. degrees. And the direction, if you notice from your vector, let's go back here. According to this one is practically your angle theta. You start from east, you go south, so that's gonna be, so you start from east, right? So this is off east, and since you go south, so that's gonna be 4.58 degrees south of east. Or alternatively, I noticed some students able to come up with these measurements on their own. That's right. It's also correct if you give the answer of its complement, which is 85.42 degrees, but the direction will be shifted. It's east of south. So this is how you solve your resultant vector using the analytic method. So I'm hoping by Monday you will be prepared for your quiz.